Good evening to everyone. Welcome to TNSET online class. Okay, today we will discuss about Unit 1, the analysis part, finite, countable and uncountable sets. Already we discussed about the elementary concepts of set theory. Okay, so already we know about what is a set and types of sets and how to represent the sets, and we have several another concepts. It's like operations on sets, relations, and functions. Based on this, today we'll discuss about some fundamental concepts in mathematics. This is very helpful for grasp the problem in TNSET and as well as UG, CSCR net examination. Okay, so based on this, first we'll discuss about cardinal number. Yeah, yes, I hope the screen is visible now. Okay, so we can start with our presentation. First, we should know about what is a cardinal number. Cardinal number is one of the important concepts in set theory. Okay, so this is very simplest concepts. If you have any set capital A equal to x plus x comma y comma z. Okay, so totally in the set we have four elements. Okay, so the cardinal number of the set A is equal to 4. That's it. Okay, so this is very simplest concept. Here we have another some examples. If A is equal to the set of all vowels in English alphabets A, E, I, O, U, then the cardinal number n of A is equal to 5. Okay, so the second one, so on each and every empty set, the cardinal number is should be 0. N of A equal to 0. And these are all the important results in cardinal number. The first one, the any non-empty set, the cardinal number is a positive integer. Okay, so this is an obvious condition. So any set, the cardinal number should be a positive integer. And the second one, and the cardinal number of finite set is finite. Okay, Suppose if you have a set A is equal to 1 comma 2 comma 3 comma 4 comma 5, this is one of the finite set. Okay, so the n of A is just equal to 5. Okay, so this is a second result. And third one, the cardinal number of empty set is 0, then n of pi is equal to 0. Okay, so this is also one of the important result. N of pi always 0. Okay, then fourth result, if A equal to B and n of A is equal to n of B. Okay, so if you have a two sets, A is equal to 1 comma 2 comma 3 and B is equal to 4 comma 5 comma 6. Okay, so in the both the set we have a 3 elements, so we can write A equal to B, then n of A equal to n of B, that is 3 equal to 3. Okay, and the final one, n of A union B, which is equal to n of A plus n of B minus A intersection n of A intersection B. This is also one of the result. And next we'll move on to equivalent set. Okay, so this is a definition of an equivalent set. Two sets A and B are said to be equivalent if there exists bijection map from A to B. Okay, so the bijection means that suppose if you have a domain and codomain. Okay, so can write 1 comma 2 comma 3 A comma B comma C. Okay, so there should be exist one-to-one mapping and as well as on-to mapping. Okay, so in this bijection mapping exists from A and B, then that set is called it as a equivalent set. Okay, so this is one of the important result for cracking the problems. Okay, so here we have one of the example. Let A is equal to the natural number 1 upon infinity and B is equal to the set of even numbers 2 comma 4 comma 6 up to 2n and up infinity. Here then I'm mapping f is A to B, then the set f of x is equal to 2x. Okay, so this is an obvious result. So bijection, hence A is equivalent relation to B. Okay, it's look like that. Okay, so here we have a set of all natural numbers 1 2 3 4 5 6. Okay, so here we have a set of all even numbers 2 4 6 8 10 up to. Okay, so here the natural numbers and even numbers. Okay, so these are all mapping from 1 to 2 and 2 to 4. It's like that. Okay, so there exists one-to-one and as well as on-to mapping. Okay, so that's why this is called as a equivalent set. Okay, so here we have some important note. Okay, so this will be helpful for cracking the problem in the easiest manner. Okay, so somebody don't know about the injective and surjective and bijective. Okay, so they might know about one-to-one, on-to, and uh, equivalent relations. Okay, so in examination part, there may ask anyone. Okay, so some year question papers we can see one-to-one mapping. Some other question papers we can see injective or subjective mapping. Okay, so we need to know about what is one-to-one and injective. Okay, so the one-to-one and injective of the same and onto the same. One-to-one and injective. This onto is another name is surjective, and one-to-one onto is called as a bijective map. And next we need to know about equivalence relation. Okay, so equivalence relation is here we have some important concept. So first we need to know about symmetric. What is a symmetric? So for example, I have two squares. Okay, so we can consider this is A and this is B. Okay, so here these two squares are symmetric. Okay, so the same area, so the same length of the sides. Okay, so this is called it as a symmetric squares. Okay, so easily we can check A is relation to B and B is relation to A. Okay, so this is called as a symmetric relation. Okay, so then the reflexive concept, suppose I can put the mirror. Here we have one of the mirror we can consider. Okay, so here I can display this A. So the mirror will display A. Okay, so that is reflexive concept. And the transitive. Okay, so here we have one of the important result, A relation to B and B relation to C. Then easily we can write A is a relation to C. Okay, so here we have another one square, that is C. Okay, so A is a relation to B and B is a relation to C, and easily we can check A is a relation to C. Okay, so this is one of the important concepts of, that is types of relations. And so this is our actual main concept, countable and uncountable sets. Okay, so this is one of the important aspect. The countable, the another name is denominable. Okay, so suppose if you have a set, here we can write. So here we have some of the natural numbers 1, 2, 3, 4, 5, 6 up to. Then here I need to take a set A is equal to 1, 2, 3, 4, up to 6. Okay. So I just we can write check A, B, C. Okay, so if the set is countable, there exists one-to-one and on-to relation. Okay, that is nothing but that is a bijective relation from the natural numbers. Okay, so our domain have a natural numbers, and this is our set. So we can put the mapping. One is mapping from A, and two is mapping from B, 3 is mapping from C, and 4 is mapping from D, and 5 is mapping from E, etc. Okay, so here we have a one-to-one mapping and as well as onto mapping. Okay, so if we can consider another one example. Suppose in our classroom we have a 10 members. Okay, so the 10 names, for example, Segar, Rani, and we have several names. Okay, so each one of the persons will be mapped to a natural number. Okay, so then easily we can obtain the count. Okay, this basic concept is call it as a countable set. Okay, so here we have a formal definition. A set A is called A is said to be a countable. There exists one-to-one and on-to mapping. That is a bijection relation between A and the set of natural numbers. Okay, so this is our keyword, and we need to check the finite or countably finite. Okay, so this is a finite. Okay, so easily we obtain. So totally we have 6 elements. So in the 6 elements are finite. Okay, so the countably finite infinite means that so the natural numbers 1 upon n. Okay, so we don't know about what is the n value. Okay, so then maybe in infinity. That is called as a countably infinite. And uncountable or non-denominable. Okay, so that is one of the opposite concept. A set which is not countable, then that set is called as a uncountable. Okay. Okay, these are all the important result. Okay, so totally we have around 12 result. Okay, so this very important concept. Okay, sometimes we can expect the direct question from this concept. Okay, so they can provide four points. Okay, so they can ask what are all the relevant concepts in countable sets. Okay, so the totally we have provided this 12 important results. Okay, then the first one is the natural numbers, integers, and rational numbers. Okay, the same positive integer, rational numbers, and this is all the countable. Okay, so the next one, Cartesian product of natural numbers and Cartesian product of an integer and Cartesian product of the rational number is countable. Okay, the third one, empty set is countable. Okay, so this is obvious result. Already we have checked. Okay, so n of pi is equal to 0. And fourth one, the set of all prime number is countable. Okay, so this is also one of the obvious result. And the set of all ordered pairs of integer is countable. Okay, so the ordered pair is already we had seen. Okay, so in the Cartesian product itself. Okay, that is also countable. And the set of all rational numbers in the interval 0, 1, that is also countable. and the set of all polynomials a naught plus a1x plus upon an power x power n is countable. Okay, so this is important result. Don't forget this result. This will be helpful for cracking the problem. Okay, so here we have one of the condition where ai is rational numbers or integer coefficients. Okay, so this is very important. And the eighth one, the set of all algebraic number is countable. Okay, so this is also one of the important result. The set of all algebraic number is countable. And ninth one, every subset of countable set is countable. Okay, so this is obvious result. Okay, suppose if you have one set, then the subset of a countable set is also countable. Okay, so for example, we have a 1, 2, 3. So this is a basic example. So the subsets are 2 power 3. We have 8. Okay, so the total, the countable set. The ninth one, countable union of countable set is countable. Okay, so for example, A is 1, 2, 3 and B is equal to 4, 5, 6. Okay, so if suppose we can find A union B, the totally we have a 6 elements. Okay, that is also countable. And 11th one, if A and B are countable and A Cartesian product is as well countable. And 11th, 12th one, A is countable, B is uncountable, then A minus B is countable. Okay, so this is important result. Okay, so we can take A is equal to countable set 1, 2, 3, 4, 5. Okay, so we can check, we can have a B. So B is a set of all numbers from 1 to infinity. Okay, so this is one of the set. Okay, suppose if you want to find A minus B, you can check 1, 2, 3, 4, minus up to infinity. Here easily we can write that is a TNSET. Okay, A minus B. So this is a countable. Okay, suppose if you want to find B minus A, that is a uncountable up to 6, 7, A. Infinity. This is a uncountable. Okay, and these are all the results in uncountable sets. Okay, so the opposites. Okay, so these are all the countable sets result, and these are all the uncountable sets. Okay, so here the irrational numbers and real numbers and complex numbers are uncountable. Okay, then second result, every interval is an uncountable. Okay, that is 0, 1. Okay, so here we have the interval 0, 1, half open interval of 0, 1 is uncountable. Okay, then the any third one, any interval in R which is contains more than one point is uncountable. Okay, so in the real field, more than one point is uncountable, and this is very important. So kindly make a note of it. You can expect this type of points in our examination. And any subset A, the relation which contains half open interval of 0, 1 is uncountable. Already we have this. Okay, then fourth one, any subset A of R which contains 0 comma 1 is an uncountable. And fifth one, if f is mapping from A to B and the range of f is uncountable. Okay, so we don't know about A and B, then the domain of f is uncountable. The sixth one, the real numbers minus any countable set. Already we have seen the previous example. Okay, so real number is one of the uncountable. Okay, so the any countable set, then obviously it is a uncountable. Already we have seen the previous example. Okay, so this is very important fundamental result. The real numbers minus the rational numbers, real numbers minus natural numbers, and real number minus an integer are uncountable. Okay, so kindly note of it. And seventh one, the candor set is uncountable. Okay, so this is also one of the important point. The candor set is uncountable. And the same, the transcendental set, transcendental number is also uncountable. And the characteristics function is uncountable. Okay, so just we can make a one note. Okay, so R minus Q N R. So these are all the uncountable, and the candor, transcendental, characteristics function. These are all the uncountable. And just we can check we'll see the some important definition. The first one, algebraic number. The algebraic number is nothing but a real number is said to be algebraic if the root of some polynomial equation, the rational coefficients. Okay, so the rational, if the polynomial equation contain the rational coefficient, then that is called as an algebraic number. Okay, so the next one is a transcendental number. The real number is said to be transcendental if it's not an algebraic. Okay, so this is an opposite. Okay, the next one is a candor set. The candor set K is a set of all real numbers x in 0, 1, which have a ternary expansion with digit 1. Okay, so for example 1.1, 1.2, let's like that. Okay, so this is a candor set, and this is a characteristics function. Okay, so K of A, if x belongs to A, then we can put 1. Suppose x not belongs to A, then we can put 0. Okay, so this is a characteristics function. Okay, so already we have seen, so this is an uncountable. So this is an uncountable, and this is an uncountable, and this is also uncountable. Okay, that means that the real number is said to be a transcendental if not algebraic. Okay, there is a coefficient, rational coefficient. That's why this is a uncountable. Okay, so this is also, we have 1.1, 1.2 like that, 1 infinity. That is also uncountable. Then the characteristics function. So we don't know about how many numbers are there. Okay, that's why. So this is also one of the uncountable set. Okay, so the next can starts with the real numbers. Okay, okay, so the real number is nothing but the set of all rational numbers and irrational numbers. That is rational union irrational. Okay, so this is called as a real number that should satisfy some of the several conditions. Okay, so in the real number, we can define the two operators and plus another one is a multiplication. Okay, so we can write such that x comma y belongs to R, x plus y belongs to R, and as well as x multiplication of y belongs to R. Okay, so this is a basic definition of real number. Okay, that should satisfies the closure property, associative property, existence of identity, and as well as existence of inverse and commutative law. Okay, so these are all the true under multiplication and addition. Okay, so this is called as a real number. Okay, the set of all rational numbers and irrational numbers that should be defined in the two operators, addition and multiplication, that should satisfy closure, associative, existence of identity, and existence of inverse, commutative law. Okay, so if that set satisfies these five conditions, then under addition and multiplication, then that is called as a real numbers. Okay, so here we have some other properties in the real field. The distributive law is true. Okay, that is x of y plus z is equal to xy plus xz for every x comma y comma z belongs to a real. Okay, third one, if x comma y belongs to R, the set of x into y multiplication equal to 0, and either x is equal to 0 or y is equal to 0. Okay, so this is one of the property or result. Okay, the next one, if x comma y comma z belongs to R, okay, that is x comma y comma z belongs to R. Okay, then x is less than y, then x plus z is also less than y plus z. Okay, so we can check with the numbers. Okay, so we can take 5 comma 6 comma 7 belongs to R. Okay, suppose we can write 5, this is x and this is y and this is z. Okay, so the first one, 5 less than, we can check a 6. Okay, so which implies that x is 5 plus z is 7 less than y is 6 and plus 7. Okay, we can check this is 12 and this is 13. The result is correct. Okay, so the same thing, if x greater than 0 and y greater than 0, that should be xy greater than 0. Okay, so for example, 5 into 6, which is equal to 30. And here, x greater than y and y greater than z and x is greater than z. Okay, so these are the fundamental result. And next, we will know about rational numbers and irrational numbers. Okay, the quotient integers are called the rational numbers. Okay, so already we have defined the previous manner as well. Okay, suppose we have, here we have one of the mathematical concepts. Okay, so Q is equal to P by Q, Q not equal to 0, then P comma Q belongs to an integer. Okay, so this is a formal definition of rational numbers. Okay, so for example, 5 by 10. So this is our P and this is our Q. So we can get 1 by 2. Okay, so this satisfies this condition. That's why this is called as a rational numbers. And here we have an irrational numbers. Rational numbers, the real numbers that are not rational numbers is called the irrational number. There is an opposite. Okay, so these are all the main irrational numbers: root of 2, root of 3, e, and pi 1 by e. Okay, so these are all the irrational numbers. Okay, so that e lies between 2 to 3. Then we have an inductive set. The inductive set is nothing but that satisfies the two condition. Okay, so here we can take this set A is equal to x, that x belongs to a real number. Okay, then 1 is belongs to A, and for every x belongs to A, then 1 plus x belongs to A. Okay, so this is a concept. Okay, so this is an inductive set. Okay, from each and every set, 1 is belongs to A and 1 plus x is belongs to A. Okay, so this is a concept. Okay, so the next one, bounded above and bounded below maximum element and minimum element. Okay, so the bounded above is nothing but, okay, suppose you have a water tank. Okay, so in this water tank, okay, so this is a maximum limit. Okay, so we can fill the water in this water tank. Okay, so the maximum capacity of the water level is an upper bound, and the minimum level of the water tank is called as a lower bound, and the maximum element and the minimum element is nothing but the maximum point on the water tank is called as a maximum element. The same scenario for minimum element. Okay, so here we have some of the formal definition. Okay, so bounded above. Okay, so a subset A of R is said to be bounded above. There is an n belongs to R. Okay, so the n is nothing but the maximum element in R, such that x is less than or equal to n. Okay, suppose I have take the value of x. Okay, so this value of x is should be less than or equal to the maximum value. Okay, then for every x belongs to A, then that is called as a upper bound. Okay, so here n is called as a upper bound of that particular set. Okay, the maximum element. So if such number n belongs to A, then that is called as a maximum element. Okay, so for example, here we can take, for example, this is x plus 10. Okay, so this x plus 10, now it's a maximum element. And the same bounded below, here we can take the m. M is a minimum element. Okay, so that is a minimum element means that the least upper bound. Okay, so here we have a formal definition. A subset AR is to be bounded below if there is a M belongs to R such that X is greater than M. Okay, so here in this example, so X is greater than M. Okay, so that's why this is a lower bound. The minimum element. Okay, so the same vice versa. M belongs to A, then that is called as a minimum element. Okay, so here we have an examples. So the set of all integers is a bounded below, but not bounded above. Okay, that is means that here we have a 0, 1, 2, 3. We know about 0. Okay, so the minimum element is 0, but we don't know about the maximum element. Okay, so the maximum element we don't know about. That's why this is bounded below. It's not a bounded above. Okay, so here we have the set of all integers. This is a neither. Suppose we can check positive or a negative integer. Okay, so this is a neither bounded above nor bounded below. We can't identify. Okay, okay, so we have minus infinity to plus infinity. Okay, so we don't know about the minimum element and as well as the maximum element. That's why this is not a bounded above and bounded below. And the bounded set. Okay, so suppose if the set have a bounded above value and bounded below value, then that set is called as a bounded set. Okay, so here we have a few examples. Okay, so A is equal to closed interval 0, 1 is bounded. Okay, so we know what is 0 and what is 1. That is a closed interval that is bounded. Okay, so then every singleton set A is bounded. Okay, so here we have only one element. Then this is a upper maximum limit and as minimum limit. Okay, so that is bounded. An empty set is also a bounded. Okay, so the non-empty set is bounded if and only if a D of A is finite. Okay, so R should be finite. Then we have a bounded set. Okay, so then we have already we have seen integer, rational numbers and real numbers are unbounded. Okay, so the integer we don't know about least minimum element and maximum element. That is so we can't find the bounded below or bounded above. That's why this is unbounded. Okay, so the same concept for rational numbers and as well as real numbers. Okay, the sixth one. Suppose the open interval of 0 comma infinity is not bounded in R. Okay, so here we can check the 0 and this is an infinity. Okay, so there do not exist bounded above. That is not a bounded. So the same 0 comma infinity is bounded in discrete the real values, and every subset of discrete real is bounded. Okay, so these are the important concepts. And the next one, we should know about supremum and infimum. Okay, already we know about what is the maximum value and the minimum value. So based on this, we can check the supremum and as plus infimum. Okay, so least upper bound is defined that should satisfy these two conditions. Okay, so the first one, L is upper bound of A and the no number smaller than L. Okay, so that is a water tank story. Okay, suppose if you take the L, okay, so L, if L is upper bound, then there are no minimum element. So there is no maximum element in this L. Okay, so that's why this is a least upper bound or supremum. Okay, so that is infimum. Infimum is already we have take M. Okay, so the M is lower bound of A, then the no number greater than M is lower bound. Okay, so that is a infimum concept. Here we have some problems. This will be helpful for crack the problem. So sometimes we can expect these type of question in TNSET. Okay, so the first problem. The first problem, you have a set A 1 by n, comma n belongs to the natural numbers. Okay, so this is bounded above but not bounded below. We will see how. Okay, so here we have a n is a natural numbers. We can get this is comma 2 comma 3 up to infinity. So we can write the set A is equal to 1 by 1. Sorry, 1 by 1 is equal to 1, 1 by 2, 1 by 3, 1 by 4 up to infinity. Okay, so here we have a the minimum element. Okay, we have a 1. Sorry, so this is a maximum value of 1. Okay, so this is a reducing sequence 1, 1 by 2, 1 by 3. Okay, so here we have a maximum element value and we don't know about the minimum value. Okay, so we can check 1 by 1, 1 by 2, 1 by 3, 1 by 4 up to 1 by infinity. Okay, so we don't know this value. Okay, so based on this, we can check the least upper bound is equal to 1. That is belongs to A. Okay, so this is our set. And the greatest lower bound, we don't know about that. Okay, so that is 0. Okay, that is not belongs to A. Okay, so that's why this is bounded above, not bounded below. Okay, so here the maximum element is 1 and the minimum element 0 is not in our set. Okay, so I hope this problem is understandable. Okay, so the second one, Okay, so the closed interval 0, 1 is bounded. Okay, so this is obvious problem. Okay, so the least upper bound is 1, that is belongs to us A, and the great lower bound 0, that is also belongs to A. Okay, so the maximum element equal to 1 and minimum element equal to 0. So that's why this is bounded. The third problem. Okay, so half half closed interval 0, 1 is bounded above. Okay, so here we have a least upper bound. Upper bound value is 1, but it's not in our set. Okay, so this is an open interval. Okay, then the least lower bound, that is 0, that is in our set, interval A. Okay, so the maximum element does not exist in this case. The minimum element exists in this case. That's why this is bounded above. And the fourth one, here we have a set. Okay, so set A is equal to 1 by 2, 3 by 4, up to 2 power n minus 1 by 2 power n. Okay, so here easily we can identify the least upper bound is 1. Okay, so that does not belongs to the A, and the greatest lower bound, so 1 by 2, so belongs to A. Okay, so this is our set 1 by 2. Okay, so here the maximum element does not exist and the minimum element is exists. Okay, so that's why this is bounded above. And fifth one is our positive equal to 0 comma plus infinity. This is an unbounded above. Okay, so in this case there is a no maximum element and as well as no minimum element. Okay, that's why this is unbounded above. Okay, so in this case least upper bound does not exist and greatest lower bound zeros also does not exist. Okay, so then the no maximum element, the no minimum element, this is unbounded above. The problem 6, for every singleton set LUB is equal to GLB. Okay, so here we have only one element. Okay, so this 0 is maximum element and as well as a minimum element. That's why the least upper bound, the greatest lower bound is equal to 0. That is belongs to A. Okay, so these are all the equal to 0. And the empty set. Okay, so empty set is bounded. Okay, so here we have a pi is a subset of 0 comma b. So for every natural numbers n belongs to R is an upper bound of pi. So pi does not have a least upper bound values. Okay, so that's why this is a bounded. And problem 7. And problem 7. Here we have a set A is equal to 1 comma 1 by 2 comma 1 by 3. Okay, so in this case, least upper bound exists 1, that is belongs to our set. Okay, so the greatest lower bound 0 does not exist here. Okay, then the maximum element is equal to 1 and no minimum element. This is a bounded below. Okay, so the next one, A is equal to open interval of 3 comma 4. Okay, so here the least upper bound 4, but this is an open interval, so that is not belongs to A, and as well as 3 is also not belongs to A, so this is a unbounded. And the natural numbers, so here we have already we have seen this type of problem. The greatest lower bound is equal to 1, but least upper bound the infinity, we don't know about that. Okay, so this is a bounded above. And problem 11, we have a 2 comma 3 comma 5 as a set A. Okay, so the maximum element 5, that is a least upper bound is 5, that is belongs to A, and the GLB, the greatest lower bound, that is 2, that is also belongs to A. So this is a bounded set. And A is equal to 1 comma 5 comma 9 comma 20 comma pi. Okay, so here the least upper bound is 20, that is belongs to A, and the greatest lower bound pi plus 1, that is also belongs to A. Okay, so this is maximum element. Okay, so this is bounded, and A is equal to pi plus 1 comma pi plus 2 comma pi plus 3. Okay, so here the least upper bound pi plus 1, and the greatest lower bound the pi plus 0, that is not in the not in our set. Okay, so this is a bounded below, and this is A is equal to pi plus 1. Okay, so the same example here, A is equal to 1 comma 1.4 comma 1.41 1.414. Okay, so this is least upper bound is root 2, that is does not belongs to A, and the greatest lower bound 1, that is belongs to A. Okay, so this is a bounded below. And the 16, the last problem, A is equal to 1 by 5n. N is belongs to an integer, n not equal to 0. This is our condition. Okay, so here we can write as set A plus or minus 1 by 5 plus or minus 1 by 10 plus or minus 1 by 15 up, etc. Okay, so the least upper bound 1 by 5, that is belongs to A, and the greatest lower bound minus 1 by 5, that is also belongs to A. Okay, so the maximum element is 1 by 5, minimum element is minus 1 by 5. So this set is bounded set. Okay, so dear participants, so as of now, we have seen some fundamental concepts in real analysis. Okay, that is cardinal number, equivalent sets, and equivalence relations, countable or uncountable, bounded above and bounded below, maximum element, minimum element, supremum, infimum. Okay, so also we have seen the 16 problems. Okay, so thank you for the today's session. I thank the Infinity Research and Development Institute and as well as Mathematics Professors Association for giving me the great opportunity for me. Okay, so tomorrow we'll cover the metric space and further concepts. Thank you. Thank you all.